Okay, so good afternoon to everybody. So thank you for your kind introduction, and I must thank the organizing committee for giving me the opportunity to be a resource person at this program. So today I will talk about fundamental quantum mechanical principles and phenomena. So I organized my presentation in the following way. Sorry. So this is the content. So first I will talk about the quantum essential principles. So out of which this energy quantization and uncertainty and the correspondence and the Pauli exclusive and wave function probability. So these all the talk about. I have made it very simplified version so that we can easily understand for all of the audience. Okay, it is somewhat a lower level. And second, I talk about some of the quantum phenomena. So one is the wave particle duality, and it's also the complementary principle which was introduced by the Bohr. Then the another three. At the end, last probably the 10 minutes, I will introduce what are the research activities we are doing at University of Hyderabad, particularly in my research group. What kind of facilities we have and what kind of works we are doing. Okay, so I'm sure that some of you, or maybe most of you, know the energy quantization. So as you know that it's like a Schrödinger have formulated in 1925-26 that this wave mechanics for the quantum mechanics, and this is the basic equation which determines the evolution of your wave function, which is basically E psi equal to H psi. Right. So if in this there are two equations, which one is the time independent, another one is a time dependent equation. So if you see this time independent, it is basically you write H is a P square by 2m plus your potential energy. And this is your psi. Here, important point here is that the psi is a spatial dependent part, and whereas this the psi where here it's a spatial as well as the time dependent part. So where you can basically get the solutions of this Schrödinger equation, and we can solve for any given problem. Okay, so this is the Schrödinger equations, time dependent, time independent. And this is what is the essential difference when we are solving any problem. But let us say that the particle is in a box where you can see that it can, when you solve for the wave functions, so you can see that how it's a ground state and the first vector state or the second excess state, how does it appears. Okay, so unless like a classical, it's a not like a it's a classical and where energy takes a continuous form, but here the particle is supposed to confine the particular energy states. Okay, so when we are trying to measure the its position or its any thing, this is how it looks like physically. You can see that when you're trying to measure, what we say is that measurement collapses the wave function. So once it is collapsed the wave function, so then it is a classical because you are definite about the particle position. Okay, it appears to be a classical. Okay, so this is the how the energy is being quantized. So if you see intuitively that this is how the classical thing is, just it's an intuitive picture, so that you will be able to understand very easily the concept that in the classical world you will have like a continuous energy values where when you're climbing, so you will be able to take. But when in the case of quantum, you see the other side, that only the particular energy states are allowed, not in between the states. So which is essential difference between the classical and the quantum when you talk about energy quantization. So another important principle, that is a energy quantization. So this is the Heisenberg uncertainty principle, which is essentially in the 1925 or 26 around. That the concept is that when you have a uncertainty in a position, when you have a uncertainty in a momentum, that will be greater than equal to always h cross by 2. So where the x and p are the position and the momentum of the particular particle. So intuitively, if you the commutation relation between the x and p, that it's always you have a IH cross IH cross. So which means that suppose in classically if your x and x position and the momentum of a particle you can measure simultaneously. So whereas in the quantum mechanically, if because the commutation is a non-zero, therefore it is impossible to measure x and p simultaneously. Okay, so that will put the fundamental limits. So which is what it's called Heisenberg uncertainty principle. So I just here showed the typical how the intuitively how does it looks like. So when you're trying to make a measurement, when you're trying to reduce the position uncertainty, which is a delta x. So when it is trying to become a delta x is a smaller, so obviously that the delta p, the momentum or the velocity distribution of these particles which are coming, it gets largely dispersed. So in the similar way, that if the delta x is getting larger and larger, so you will see that the particles which are flowing through this is more uniform velocity distribution. So one typical example I can give is that in relation to the this one delta x and delta p, that suppose if you flow the water in a pipe, so suppose you are twisting the pipe at or the pressing the pipe at the center. So before you press, you see that all the particles have a uniform velocity. But when you are pressing at the center, you see that there is a distribution of velocity, because you are trying to kind of minimize your delta x by pressing it. So it introduces your uncertainty in the delta p. So basically what I'm trying to say is that the product of this delta x and the delta p, no matter what you do, that if you try to improve the precision in the position, there will be a large dispersion in the momentum. But when you try to improve your improve the precision in the measurement in the delta p, which is a momentum, there is a large dispersion in the position. So because these two products are greater than or equal to h cross by 2, so therefore this product is being maintained with the h cross by 2. So depending upon the delta x and delta p, so if you know one quantity, you can calculate the other quantity. So this is what the essential physical understanding of the Heisenberg uncertainty principle. So the next important principle is the correspondence principle. Correspondence principle, basically you think like always we will wonder that what kind of system would behave like a quantum, or what kind of system would behave like a classical. In principle, actually, it is everything behaves at. Everything in everything you have a quantum mechanics is involved. Okay, it's only that at what scales you are basically sort of observing the effects. So when the system evolves, large number of particles, like say like you have a 10 raised to the power 4 or 10 raised to the power 5 or even more, or the higher energy levels, essentially it is when you're basically going large ensemble of systems. It's essentially it's like a classical system, but it's one of the special case of the quantum mechanics. Okay, when what we are seeing at our daily life in basically it's everything origin is a quantum mechanics, but what we are experiencing or what we are observing, seeing is a quantum effects. If you go to the deeper into the level. Okay, so here you can see this is the where the when you increase the quantum number. So basically, when you increase the quantum number from the n is if it is a very small, then you are essentially we are going to the particular energy, well quantized energy levels, which is n is being small here. You can see when n is being small, here you can say n equal to 1 or n equal to 2 or n equal to 3. So how the wave function has been sketched as a function of position. So which is a mod psi x square. So you can see the finding a probability of the particle within the this thing. So and also when n equal to 2 or n equal to 3. So once the moment that n is becoming larger and larger, obviously when you say n is becoming the infinite, then it is like a no particular energy states. It's all it is a when in the classical limit, when n is being n is being extended to the infinite, what will happen is that rather than having the well quantized levels, you will have a energy of a continuous spectrum. So which means that all the energies are there continuously rather than the discrete. The correspondence regime where you are in between the quantum mechanics or the classical limit, quantum limit and the classical limit, for the when you increase the number, principal quantum number n, so you will see that at some places they can quantum crosses quantum enters into the corresponding regime, and also it will leads to the classical mechanics. Okay, so this is basically the correspondence regime is where you can see that here you can see you have well quantized levels, as well as when you go to the higher n number, so that spacing is also coming down to the smaller and smaller. So that's how it is being connected from the quantum mechanics to the classical mechanics. But this is how the typical examples I could give. Suppose you take a hundreds of particle and you put it a box size of a smaller, so that particle will have a certain energy states to be occupied. But when the box size is becoming bigger and bigger, these particles will have if it is a infinitely bigger the box size, then the particles will take any value of energy, because they behave like a classical system. So which means that continuous energy states are available to occupy the particle anywhere in the box. But when it comes to the particles, the box size is getting smaller and smaller, you will see that the particle can take only the particular energy states. This is how we can physically visualize. All right. So another famous principle, which is a very, very important, that Pauli's exclusive principle, which is very, very important role it plays. It depends on the, it says that one is the spin up and the spin down the electrons. What it's that states that no two fermions, like either it's a electron or proton or neutron, can occupy the same quantum state simultaneously within the same state. So if it is what it physically means, that if it is one is up and another one it has to take it down. So they cannot occupy the same state. So why that is matter? Because why it is very, very important. So here you can see this is the reason why you see the solid is like a solid piece. So it prevents that the collapsing electrons from into the same space. Okay, which disturbs the disturb the structure of the material. Okay, so therefore, one electron, if it is occupied plus half, another electron it will occupy the minus half. So one is up, another one is down. Similarly here it is a pictorially. So one, it is shown the spin direction up, the another direction is down. Okay, so they don't take in the same quantum states. One, if it is a one is taken up, the other one will takes down. So as a result, it can form a matter which is periodically arranged in the solid state systems. All right, this is a very, very important principle. So the last principle which I have want to bring the attention, that unlike in the classical system, so where you are definite about a position of any particle, okay, so in the quantum systems, the states usually represented by the psi, which is psi is a function of position, which is r and t. Okay, so it's always we don't know where the particle it is. Okay, unless you make a measurement, what happens is that it is represented by psi, right? So once you make a measurement, that is basically it is a probability that mod psi square will give you the particle probability at specific location. Okay, suppose if you are measuring at the particle at this, so you are going to get a maximum probability of finding a particle. Suppose if you are measuring the particle at this stage, that it's going to give a certain probability. It is always the probability distribution what its psi determines, because you don't know the definite position of the particle in the wave packet. Basically, it has a probability distribution of 0 to a maximum, which is a 0 to 1, which you can have different probabilities. Please remember that once you make the measurement to find the particle position, so you are definite about it. So which means that it's a wave function is got collapsed, then you reach to the classical picture. Okay, before you make the measurement, it's a quantum, because you don't know where the particle is sitting. So it can have a different probabilities at different positions. Once you make the measurement, you are definite about it. So your outcome is definite. So that's where the crucial role it will play in the wave function and the probabilities in the quantum mechanics. All right, so then these are the principles of what we have talked out of the things. So the principles what we so far we talk is the wave function and the probabilities. Then the phenomena, corresponding phenomena, is that what are the consequences by having that kind of principles. So one is that wave particle duality, and also it's a complementary principle. Okay, so I think you already learned that photon can behave like a particle as well as the wave nature, right? So most important thing I want to kind of emphasize here is that, see, photon can have a can behave like a wave as a particle nature, but most important thing which the Niels Bohr always had a stressed upon is that both simultaneously it is not possible to exist. This is what you have to say. At a given point of time, in a given system, okay, all right. So when you have either you have a wave nature, which is shown here, or you have a particle nature, okay, at a given point of time or at a given space in a same system simultaneously. So what I'm trying to say is that always we talk about wave particle duality, but we should not miss the point of the complementary principle is that in all quantum systems, okay, dual nature is exist, but these two aspects, these two wave and the particle nature cannot be observed simultaneously in the same system. Suppose at some point of time it behave like a particle, and other point of time it behave like a wave. But simultaneously it cannot behave like a wave and the particle. This is what one must understand. So in experimental proof, it's given it's a diffraction experiment that cannot be done. That recent also experiments are done with a single atom and a single photon, they have proven that you have the either you have a wave or the particle nature, but both simultaneously it is not possible. That's very important. The best way to kind of intuitively understand this wave particle duality is that I always give one example that I'm sure that most of you are playing the caroms, right? So when you hit the striker, okay, when you hit the striker, so you see the striker as a point, okay. The moment it hit to the striker to the coin, so the coin will sort of make the wavy nature, right? So in the what I'm saying is in the carom board, you can see that both particle and the wave nature together. But at a given point of time, the striker is only one. But if you leave it in the over the time, so you will see that wavy nature is also it is making. Therefore, it is both are there. It's like you can intuitively think of in that way. So basically, that is how one can think of it. Then another powerful and also most important thing which you always find applications in the quantum mechanics, and nowadays most of the quantum technologies are based on this superposition principle and the entanglement. Okay, so this is, I want to clearly tell, this is very important to understand that let us say that you have a classical bit. So this is like either you have a 0 or 1. You are always definite about either 0 or 1. Okay, but whereas a quantum, the difference I want to tell you that it is a superposition of 0 and 1 with the probability amplitudes of alpha and beta. Okay, this is basically it is a state vector which is running over the Bloch sphere. Okay, so between the 0 and 1 with the different probability amplitudes alpha and beta. So if you take mod alpha square plus mod beta square, it should converge to 1. So suppose if you have a mod alpha square is a 0.5, then you should have a mod beta square is also 0.5. Okay, the superposition makes the quantum mechanics so powerful. Okay, so whereas the classical, you are definite about it. You are, suppose if you say 0, you are 100% that your state is a 0 you have. But if you say it's a 1, you say it's a 1. But whereas in a quantum qubit, so it's a superposition of 0 and 1 with different probability amplitudes. So mod alpha square plus mod beta square. Okay, so this makes very powerful for the variety of applications. Okay, so just I want to give you one example that where you can basically imagine or you can see the superposition of this thing. That let us say that you have a point A and point B. You want to reach point A to B in we have, let us say, 10 variety of ways to reach point A to point B. Okay, but what you know is that only one way is open, all other ways are blocked. So classically what will happen is that when you start from point A to B, so first it will see the system will evolve through the first one, and if it is blocked and it will come back, and if it is goes to the second, if it is blocked and come back, and if it goes to the third, it will block and come back. So which means that every time system will evolve through the different ways. Whenever it is opens, it comes out, right? But whereas a quantum, the advantage is that when you're trying to go from A to B, the state has a superposition of all 10 possibilities with equal probability. Okay, so it means that it will verify in 10 ways simultaneously. So whichever way is open, it will come out. So that means that your computation speed or your achieving the achieving or reaching the other side is much faster compared to the classical. So this is happening because of your initial state itself as a superposition of all possible ways from point A to point B. Okay, with equal probabilities. Okay, whichever way is open, it will come out and will give you the fruitful result. That's the essential. Physically one can understand. The key intuition I want to bring here is that you can understand very much, very layman understanding, that classical bit is like a coin lying on the flat, right? So if you take a coin, if you put it on the table, it's like definite about it. Either it is heads or tails. There is no other possibility, right? So you will have head or the tails. Okay. But in a quantum mechanics or in qubit, how you understand is that you take that coin on the table, you rotate that coin on the table. So it makes the possibilities of all, right? Either it can be anytime it can be head, or anytime it can be tail. But how do you know that, which one comes, or whether it's head or tail? So for that you need to measure it. Okay. So you need to measure the system, then you will know the outcome. Okay. Until you measure, again I am saying, I am repeating, I repeated in the previous this thing, until you measure it, so you don't know what is the state of the system. So once you measure it, you are definite about the system. This is the most important thing. So which means that the spinning coin on table, it's a mixture of mix of both head and tail, which is a superposition of both with a alpha and beta probability amplitude. Okay. So once you measure it, you are definite about it. That's the essential difference. I hope you understand the physical meaning of it. And another most important thing is that it's a very, very powerful, nowadays people are realizing experimentally, it's a quantum entanglement. Okay. So quantum, this is the superposition, previous one, this is the entanglement. Okay, which is classically it doesn't happen in most of the system. It's only the quantum mechanical property. So let us say that you have a laser, you have a nonlinear crystal. Okay, when you send a laser to the nonlinear crystal, so you will generate two photons which are entangled. So one is the vertically polarized photons, the another one is a horizontally polarized photons. Most essential part, okay, most important part of the entanglement is that, suppose you measure this photon polarization. Let us say it is propagated, it is a quite long propagated, two photons, we say it's one is a signal, another one is idler. So you measure any property of the beam, the signal. Let us say that you measure the polarization of that photon, it is vertical. So you can tell the other photon polarization without performing any measurements. Okay. So if you found that in one it is a vertical, the other one has to be in horizontal. So if you found that one is the horizontal, the other one has to be a vertical without doing any measurements. Okay. So it's like both are correlated. Both the things which are originated from this crystal, when you send a high intensity laser beam, so when passing through the nonlinear crystal, so either you have a vertically polarized light, which is a signal, we call it idler, it's a horizontally polarized light. So both photons which are coming out of that crystal, both are entangled photons. So this process is what it is called SPDC, like a spontaneous down converted photons, which is commonly used in the world for the quantum applications. Okay, so you can see it's not necessary that it has to be photon. So you can think of like two entangled electrons. Suppose one is a spin up, another one is a spin down. So if you have one spin up and it is correlated with the other electron, so that means that if you perform the measurements in one spin up electron, then automatically, instantaneously, you know the other electron is in down. Okay, so one is up, another one is down. So it's instantaneous. You don't have to do the experiment. That is what the powerfulness of the quantum entanglement. Okay, so that's here it is shown here that if you see in the third one, if you say left side, it's the other one is the right side. So if it is a one up, another one is down. It's like how you make the entanglement, which is a very, very powerful application in the quantum part, which is opening variety of applications, which I'm going to tell you where it is. And this one, I'm sure you know this one, that quantum tunneling, you might be solving the problems on quantum tunneling. It is a very simple that in the classical wall, if you see, it's like, think of like this. Like if you throw a ball at a wall, what will happen is that it will bounce back to us, right? So, but here in the quantum wall, there is always a small probability that the particle can tunnel, okay, tunnel through the energy barrier. Okay, this is the phenomena which is have a lot of application in the other things. Okay, so you see here, I mean, this is what it's pictorially I have shown here, so that you will get intuitive understanding what I mean for the quantum tunneling or the quantum mechanics, which plays a powerful role. That when you have a barrier, let us say that your energy is much less than the barrier height. So classically, you cannot jump over that barrier, right? Suppose you have a 10 feet of or maybe 20 feet of wall and you are trying to jump that one, or maybe 100 feet of wall. So the classically you cannot go to the other side of the wall. But quantum mechanically, no matter when you have a barrier height is how big it is, then when you have a energy of this E, which is in this area it's a greater than V, and in this it's a less than V, there is a definite probability that you are tunneling through the barrier. This is how pictorially you can see. It's like a to give a intuitively I have drawn here that this is your barrier height. So when wave is passing through the barrier, so you see that definite probability of a transmission and there is a definite probability of the reflection. Okay, this is what it is called. It is a quantum tunneling. So classically, you would not expect that if the barrier height is too high, that you would not expect compared to the energy of the particle, you would not expect to appear this particle to the other side. But whereas the quantum mechanically, it is possible just tunnel through the barrier with a definite probability that if you work it out, if you write the Schrodinger equation and solve for it, then you know what is the probability of the right hand side, what is the probability, which is a transmission it is usually called, and the other side is a reflection that you can know easily. So you can get the probabilities of finding the particles. Okay, so these quantum tunneling has a powerful applications typically I have summarized here few, but it has a powerful application in other things as well. So this is I brought since I talk about this classical versus this quantum, so or mostly the quantum powerful concepts. So in classical, what we say that we have a definite state and you know the thing about it, but when it comes to the quantum, you always have you're not definite about the state. So always you have these superposition, right? So when this is the what aspect is what we are referring here, and what is going to happen in the classical world and quantum world. So in the case of state, so it's a well-defined position and momentum. It again, as I said, in the quantum world, always it's a superposition of states. That makes the powerful of the quantum world. So because it can exist in all states simultaneously with equal probability. Okay, so that is very good for the quantum computing. So when the measurement, when you are trying to measurement in the classical, it's a passive and precise because you know the definite about the things, and also it is non-disruptive. Most of the time you don't disturb the classical system or you don't perturb the system quite severely. But whereas the quantum world, when the moment you make the measurement, so it can collapse the quantum states, then you can give the outcome. Once the state is being collapsed, then you will get a outcome, the measurement. So the predictability or the equation of motion, so you can deterministic, because it follows the Newtonian in the classical world. And whereas the quantum world, it is again the probabilistic outcomes. So it's a how probable it is. And information which goes, like a 0 or 1. So you will say, so bit is 0 or 1. So you are definite about here. Either you will have a 0 or 1. There is no superposition of 0 and 1. But whereas the qubit case, it's a classical bit, either 0 or 1. Whereas a qubit case, you can have a 0 and 1 with simultaneously. What I mean simultaneously, again, that you will have a 0 with a probability amplitude of alpha and 1 with probability amplitude of beta. Okay, so when we look at the length scales, okay, so it's when you see the classical world, what we are living in, what we are experiencing, basically it's a macroscopic objects, you see the classical world. Whereas a quantum world, that it's a single atoms or the photons or in the much smaller length scales. Okay, it's almost the atomic length scales which we are observing. Basically, these two worlds are connected, but if you see the macroscopic objects, so if you go to the deeper into the smaller and smaller size, then your quantum effects are becoming significant and significant. Significant and significant. All right. So then with these concepts, with these principles, the first quantum revolution have already been established in the 20th century from 1900. So the key ideas which we already discussed, that wave particle duality, energy quantization, or the atomic structure by variety of various scientists, that is a first quantum revolution. So what we are having is the second quantum revolution, which I am going to tell you in the further slides. That the major outcomes, it's like to explain these lasers or the semiconductor, MRI and atomic clocks. These are the major outcomes of the first quantum revolution. So basically the nature of the control is that all quantum effects are indirectly, basically mainly at the statistical or ensemble level, not by individually controlling the quantum states, which I mean to say that it's not individually you are controlling the single atom or the single electron or the single photon. Okay, those in the 20th century, most of the time you have a ensemble of the emitters or ensemble of the things. Okay, and this made an impact of the foundation for modern electronics and photonics, or where we today get most of the information or the communication technologies. Let us say that today we are receiving the internet into our offices and all the things, consequences of these all the applications. This is what is quantum revolution in 20th century, starting from the Plancks to the all other eminent scientists. And what we have now what it is going on is the 21st century. What we are having is, as you know, 2025 is the 100 years of quantum mechanics. So the second quantum revolution, what we are having. So we are exploring the applications of the further I have discussed after the few after the few principles, which is a superposition, entanglement, as well as the coherence. Okay, so the presently we are into the second revolution. Okay, which is currently it's going on. Okay, it is basically the mostly towards to the experimental progress of realizing this quantum superposition and entanglement and the coherence. Okay, the key point here I want to tell you that in the first revolution, most of the things you have seen as from the ensemble or the statistical mixture of the effects. But here present nowadays, people are working directly get the control of single quantum systems. Individual. That's more important things. Okay, so which is a single atoms or photons or ions or qubits. Okay, it's not like an ensemble. Everything is a one atom or the one photon or one ion or one qubit. It's a single, which makes the experiments somewhat difficult. Okay, so then these are the what are the essential principles which are exploring in this thing is that it's a superposition, entanglement, and the coherence part of it. It's a observed effects which people have already demonstrated some of the effects. So what are it's going to enable the technologies? I mean, how you are going to get take the advantage of that physics into the technology? The first powerful application is the quantum computing. Okay, so quantum computing is like, as of now we have a classical computing, which is that's what I gave you the example, that to solve one problem in a 10 different way, if you have a quantum computing, it can solve it immediately, because your initial state is a superposition of superposition of all, with all possibilities with equal probabilities. And also you are going to have a quantum communication. Okay, so quantum communication means that as of now we have a security issues, because when you send information one place to another place, so you if any third party try to measure the information, they can easily tap the information and get the information. But when you are sending the information in the quantum states, it is impossible to break that information, because the information is in the quantum state. When somebody is trying to make a measurement on the system, the wave function will get collapsed, then he loses this information. So it is not possible to steal the information. And most important, another thing is the quantum sensing, which is a more apt for this present workshop. I think the other people will talk about more experiments on quantum sensing, which plays a powerful role, and also the quantum simulations. So these are the how it is four verticals. Our second quantum revolution has been established or establishing. So these are the our Indian government also investing or already invested large amount of money to accelerate the research and products in these four areas, which is essentially quantum computing and communication and sensing and metrology and material and devices. This is which is very important. Then what kind of impact it will bring? Okay, so the most, this is we are going to have in next 5 years or probably the 10 years, we are going to have a disruptive technologies in our lives. So this is what the scientists or the eminent people are predicting, that once these quantum effects or the quantum devices come into the society, so we are going to change our lives in a very differently, which does not exist in the previous classical system. Most important is the computational speed is really high and security is really high. So you can send the information with a really high confidentiality. And also all the measurements are done in a quantum, which crosses the classical limits. It's like a Heisenberg uncertainty limit we can reach in the quantum systems. So I think this is the what I would like to give overview. Sorry. So this is the second part is finished, the quantum phenomena and how the revolution started. And this is what we are doing at University of Hyderabad. I will not take much time. I think within 5 minutes I will close. Okay. So let's have a discussion on the questions. That we are at University of Hyderabad, we are doing a quantum photonics research. We are doing experimental research work. This is our research group. I have about 5 PhD students, and recently 2 students graduated from our group. Then they are working at different places in the world in the quantum technology and related areas. So at our University of Hyderabad, so we have established the facilities. So in order to see, if you want to do experiments, we need 2 things very, very important. So one is the manpower. This is what the manpower we have. Another one is money. So we write proposals, and the ministry or the funding bodies gracefully approved our proposals. Then they funded us some amount. Then with that amount, we established a variety of the facilities at University of Hyderabad, which is accessible to the all people in the country. So before we start any experiments, we usually computationally design what kind of necessities are there. So therefore, so that we know what we will predict in the, or what we will expect in the experiment. Okay, so therefore we have a computation facility where you can design all the systems, and our students can easily do these things. And the most important thing in this quantum experiment is that we should have a clean atmosphere for the experiment. This is a very, very crucial requirement, because just imagine that we are working at the scales. Okay, scales, just I want to give you one example that typically human hair size is 60 micron or 50 to 60 micron. We are working with the nanoscale sizes of 100 parts of human hair. So which means that if you have a hair dandruff which is falling onto the structures can kill the properties, optical properties of the structures. This is the very important. So therefore we keep the clean atmosphere so that the quantum effects can be seen very effectively. So this is the most important thing we have realized. And we are making the micro nanofiber fabrication for the quantum applications. So this facility, we have a first of its kind facility in the country. Okay, so this is the it is essentially it can make 125 micron fiber, so you can get it down to the half micron, so which will be useful for the quantum applications. So in order to manipulate the micro nanostructures, so you can use the nano and nano positioning stage. This stage can run with 50 nanometer. So if you want to manipulate them in the inverted microscope is required, because so you can view from the downside and from the top we can manipulate the systems very effectively. So we have established the facilities inverted microscope system. And for the most of the quantum application is that normally when you want to handle the quantum things, always you should pick up a very small quantity. So we have established, suppose this is like a nano spatula. Like if you have a normal spatula, so you will not be able to pick up more precise than the microliter. But here what we developed is a system that you can even pick up a sub-picoliter solution you can pick up from the bottle. So that's what we have developed to see the quantum effects. These other two facilities which is very important for the quantum is that, so how do you say that some photons which are coming from the source, how do you say that you have a quantum nature or the classical nature? So we have indigenously developed the system, what we call it is a Hambre boundary setup, where you can make a quantum correlation. Then you can say that you have a quantum system or the classical system. It's a temporal correlation, so which is developed at our place. We are working on that to measure the single photon nature. And the other facility what we have is that not only the temporal. So how do you, in ideal case is that we want to have a indistinguishable single photon, which means that suppose the photon which is coming now should be the same as the photon which comes later in terms of frequency. In order to know the frequency spread of the single photons, so we have established the facility. This CCD camera can measure the single photon frequency with a very high precision. These are the facilities what we have. It is accessible to everybody. So if anybody wanted to use this facility, you are quite welcome. And thank you very much for your attention. Now I would like to have a questions on the topic what is being discussed here. Hello.
Thank you, sir, for your wonderful lecture and me sharing the facilities that you have.
Yes.
So now I encourage the participants, please submit your questions through the chat box. So I think I can see one question. Can we disapprove the Heisenberg uncertainty principle using quantum technology?
Wait, I can't see anything.
This is in comments or chat box. This Sankar P.
Yeah. Hold on a second. Yeah. What was the question?
Can we disapprove the Heisenberg uncertainty principle using quantum technology?
No matter what you do, you cannot cross the limit of Heisenberg uncertainty principle. This is what I want to clearly tell you. Thank you for the question. It's a very interesting question. No matter what you do, that you can't break the Heisenberg uncertainty principle. So people often misunderstood that when you have a delta x and delta p is greater than or equal to h cross by 2, that they are trying to measure in delta x, but they are not about delta p. Then they claim that they are measuring better than the uncertainty principle. It's no. Okay, this must be emphasized so that, so that suppose you are squeezing the precision in one direction, the other delta p, it is getting diverged. Always your multiplication of delta x and delta p is greater than h cross by 2. You cannot go less than h cross by 2. Is that clear, Shankar? I hope you understand the point. People individually, if you measure delta x, then they may claim that they're saying beating the uncertainty limit. Actually, it is no. It has to be seen in the product of delta x and delta p. That product is always is greater than or equal to h cross by 2. Right. It is often it's like a miscommunicated or misconception that people understood in that way, that quantum systems will beat the uncertainty principle. Actually, no. Yes, sir. Any other questions?
Another query is by Usha Desai, how quantum communication is more secure.
Usha Desai. Yeah, thanks for the question. See, presently the present communication is a classical. It's like you're sending like a classical bits of information and 0 and 1. So you are definite about the system, either 0 or 1. Now, if the third party comes and tap that information, he will get that information. Okay, so because you are definite about the information. Whereas a quantum, so because the information is sent in the quantum states, always it's a superposition. When somebody from the third party is trying to measure the state, the wave function will get collapsed. That means you are losing the information. So the other party will not have the information about what is being sent. This is what it must be understood. Okay, so therefore, in that way, you enhance the security from the classical to the quantum. Is that clear? What was the name of the question? Usha Desai. I hope it's clear, right?
Then, sir, another question: how the quantum entanglement concept in quantum teleportation by G.V. Prashannan.
Okay. How the quantum, yes, people are using it. I am not into that field into tell the very clear details, but people are using. So important point here is that when you have an entanglement, when you perform the measurement on one part of the things, you automatically know the other part. So without measuring anything, that concept they are using in that teleportation. Okay, specifically, I will not be able to more details I will not be able to give because that field is emerging and many people are working in that direction.
Then one more interesting question: how much will be the approximate total cost for the lab facility that you have listed?
Oh, so it is approximate cost all facilities around 4.5 crore. 4.5 crore, the lab facility what we have in our University of Hyderabad at School of Physics.
Maybe, sir, last question.
Yeah.
Could you please explain nuclear magnetic resonance in quantum technologies, scope of research in this area?
I'm sorry to say I'm not very confident about that application and all the thing because I never worked on the that part. Actually, there are NMR people who are working in technology. It's like it's a spin manipulation and of the system. So that comes somewhat as solicited people who are doing it. Frankly speaking, I don't know deep understanding in that field.
So thank you, sir. I hope you can get sir email ID from the internet. One participant asked we want to visit your lab and see at time.
Welcome. Not
So-
one. All of you, anytime, please write email and come to our lab. Please, please. Also, it seems like he was asking contact number. I think email ID. Our organizers have my both contact number and email ID. Could you please share with them, participants?
Sure.
Yeah,
I will
yeah.
say.
Anytime, please. Anytime. Don't hesitate.
So,
Please
sir,
come and
on
support.
behalf of participant as well as my personal behalf, I again thank you for your time and giving this wonderful lecture today. And hope to see you soon for your next lectures.
Sure.
And once again, thank you for your time and this lecture. Now, I think this is the time to introduce our second speaker, because we are just having 4 o'clock now.
Right.
I hope, yes. So, Dr. Aswad Babu, sir, he has already joined. So, the
Can I
second,
exit?
yes, sir, yes. So, yeah, thank you, sir. Thank you, Yula, sir.
Thank you very much. Yeah, thank you.
And today's second lecture, that is based on this implementation, atomic resonance, superconducting Josephson effect, and population inversion. And the lecture is given by Dr. Aswad Babu, sir, Department of Physics, IIIT Dharwad. You already interacting him for few lectures he already covered. And today he's going to talk about this implementation part. So, sir, I welcome you for today's lecture, and I hand over to you, sir.
Good afternoon, Avasti sir. Good afternoon, all the participants. You had a wonderful session. I was fortunate to be there for a few minutes before. I could see Dr. Ramchandra has discussed the experimental realization of the quantum effects. That is very nice. Participants might have got the perspective of the experiments even through this module. Okay, so let me start the session, my session. Okay, so last time we were discussing, just a minute, let me share my screen.
Sure, sir.
Yes. Okay, 1 minute. The implementation part we were discussing last time. So in that we were discussing about various kinds. Okay. So number one, what we discussed as per the schedule, the implementation, we discussed some atomic resonances and a little bit of superconducting Josephson effect and population inversion. So the population inversion we did not do in detail. So what I will do today, I will just discuss into the more details, the population inversion. Okay, right. So 1 minute. Yeah. So I'll use the PPT, and at the same time, I will use my handwritten notes to describe things in more detail using a blackboard writing. Yes. Okay. So let me see what I have in my PPT. So the population inversion is very much the very important recipe of lasers. You see, laser systems, they purely rely on this process. Okay. So, which means we need to understand that in detail. So these days, lasers are there in every equipment for the precise activities. We need these lasers, right from printing. You see, paper printing. For example, we want to print something. There are laser printers, and you want to cut something with a precise manner. Lasers are involved. So lasers is a fundamental entity in our day-to-day life in all the equipment. So since they rely on something called population inversion, so we want to get into the details of what is population inversion. Okay, right? So here I have, in general, in thermal equilibrium, means the system is led to remain stable, for example, at the ambient temperature. When I say system, what is a system I'm talking about? Let's say atom having nucleus and the electrons around in their orbits, several orbits. Okay. In that, let's say I'll pick few orbits which are required for my attention. Okay, few particular orbits. So those orbits I will be drawing them as 1 minute, like that. Okay. So let me call the orbit n1, n2, and n3, and so on. Okay. Just for the simplicity, I am drawing the orbits roughly of the same separation. Okay. So when it comes to naturally occurring atom, the orbits may not be equally spaced. They are non-linearly spaced. For this understanding, I'm just drawing here like this. Okay, at the thermal equilibrium, means at the ambient temperature. Okay, so what happens usually, the electrons are placed inside an orbit which is close to the nucleus, more of them placed. Okay, which means the ground state is very much populated to a greater extent. Okay, right? So excited state few may be there, but not many. Compared to the population of the ground state, obviously the like a higher order states are always less than in number. Okay, so that is the thermal equilibrium situation. But we need to have something opposite of this. What is that is, at thermal equilibrium we will have n1 is much larger than n2. N stands for number of electrons in a given orbit. Okay, that is the thermal equilibrium situation. But in to have a lasing phenomena, we'll see what is a lasing as we progress through. To have a lasing phenomena, we need to have n2 much larger than n1, or at least larger than n1. Means more number of electrons are required at the excited state to have, okay, a lasing effect. Okay, so before going there, this is just a core principle I'm trying to give. So this represents a non-equilibrium condition essential for light amplification. Okay, so that also we'll see how light would be amplified having n2 larger than n1. Okay, so in a way it violates a natural Boltzmann distribution at any positive temperature. Okay, right? So we'll see that how it could be understood. So first, let me understand at a core level what I mean by, okay, electrons being in the excited and then ground state, excited more, and all those things. Okay, first of all, let's take two orbits of an atom. Okay, let me call this a ground state and excited state. Okay, let's say at equilibrium we will be having some electrons in the ground state. It is obvious. Okay, right? Whenever I supply or incident a photon whose energy is exactly matches with the energy separation between the ground and excited. In that case, what happens? The electron just excites, go to the higher order state. Okay, when it goes to the higher order state, okay, after 1 microsecond on an average, that is a lifetime of excited state, the electron would spontaneously on its own, it just decay or transfer, right, de-excite to the ground state. When it de-excite, whatever excited energy it has, it emits that energy. Okay, it is called spontaneous emission. Okay, spontaneous in the sense on its own it is emitting. Remember, the amount of energy emitted is exactly the same of amount of energy it has consumed in the first place. Okay, right. So now the spontaneous emission is happening on its own. Okay, I don't have any control on which direction it is emitting. Okay, and if I take a atomic vapor consisting of several atoms, when I incident several photons onto such atoms, we don't know which atom got de-excite, like spontaneously emitted in which direction. They are like uncontrolled manner, they emit in all the directions. Okay, the next thing is, let's say I have, by nature or by some manner, let's say somebody already excited few electrons to the excited state. What I mean is, before I do some experiment, the electrons are already there in the excited state. Let's say somebody excited and they left it there. Okay. At that time, if I send a photon of same energy, matches with the separation between the ground and the excited state. Now you see, the h mu doesn't have any role here, because already the electron which is consuming the photon, it is already in the excited state, that guy. Okay, the intuition of our says the photon comes in and just leaves as it is without being bothered by any atom here or electron here. Plus, okay, please mind here, what happens is, this photon, instead of traveling on its own without minding anything here, because that has no business here. Okay, in the sense there is no one to observe, but what this guy does, somehow it disturbs the state of the electron, the excited state of the electron, to fall to the ground state. What happens is, along with the photon which is incoming, the electron in the excited would falls to ground state, and that would emit the photon of h mu along with the photon which is there in the first place. Now you see, two photons are emitted. Okay, so what is the role of the second photon? The photon which sent in the second experiment is, its role is to just trigger this emission from the electron, so that I get a photon energy. Okay, now if you see here, the emitted photon and its direction could be controlled. How we can control? Using a incident photon. So this process is called stimulated emission. Okay, I am actually stimulating the system to emit in a particular direction. Okay, so this is a process, stimulated emission. Even before this too, one process which we have to think is absorption. What is absorption? Photon is being absorbed, electron goes to excited state. So there are three processes which we covered here. Number one is a photon being absorbed, electron goes to the excited state, and an excited state may comes down on its own to the ground state and emit the photon. And by any means, if the observed photon is already there, and that photon, so electron is observed, electron is already there, now incoming photon would trigger a stimulated emission. So that is the third process. Okay, now advantage of having the stimulated emission is, I can trigger the emission in a particular direction. Okay, so I can streamline the bunch of photons coming in a particular direction. Now I am just to talk in terms of a single atom, single photon coming in. When the experiment is performed, it is all collection of few billions of atoms per se. Atomic vapor is taken, a bunch of photons were incident onto such atoms, and then you'll see a spontaneous and stimulated emission. Okay, so now let's get back to the PPT and see what it has to say here. Okay, Fine. So in the case of lasers, okay, 1 minute. We have in the case of lasers, laser operation enables coherent light emission. Means, what is a coherent light for you? Coherent light is if I have a laser light coming out, if there is a laser light is coming out, if I just take any two rays, okay, so any two rays, if you just consider, there exists a fixed path difference and phase difference. What is a path and phase difference? I mean, both are same. Described in terms of path means in terms of wavelength, phase means in terms of frequency. Okay, right? So in the terms of path means one ray peaks at one point, another ray peaks at another point. There is always fixed path difference. Okay, delta p, let's say path difference, or delta L per se. Okay, let me take it as delta L. So this delta L, when the two waves peak, always in a fixed difference. So you measure at a very starting or measure at the very late. Even in that case, the path difference or the peak differences remains to be same. So, which means they are actually traveling in a same synchronization. It's like if you see the March past, okay, during August 15th or Republic Day in Delhi, you see the military personnel will do the march past, right? Even though the heights of the people are very much varied from start to end, but they all move in the same manner. The legs and the hands movement is in synchronization. So in the same way, the first ray may peak little bit earlier, second ray may peak it little later, but the difference between when they will peak, let's say first ray peaks, let's say after 10 seconds, second ray peaks after 12 seconds, how much time difference is a 2 seconds difference between their peaks. This is in time I'm talking about. So in time, this 2 seconds separation always remains the same as long as the rays travel to any distance. Okay, and that is a coherence for you. Phase difference or a path difference. Okay, phase could be explained in terms of frequency and time, and path difference would be explained in terms of the wavelengths where it is peaking. Okay, that is a coherent light source for you. Now this is a laser lights, one of the characteristic, and this is possible with the optical cavity, okay, where the resonance is sustained. Okay, so what is this is, you take a cavity, means mirrors, let's say concave mirrors, you put atomic vapor inside, okay, and you excite by incidenting some photon, or you can do heating, you can do excitation in any form, right? And you incident a stimulating photon in such a way there is a in a trigger of stimulated emission where the photons were emitted in particular direction, and they go back and forth and they emit in one direction. Let's say we have a small hole on one of the mirror, and the light emits from that point. Okay, so the way that mirrors are arranged, the distance, right, that is also plays the role, like a laser cavity, right? And moreover, here I can create a monochromatic light using this population inversion. Monochromatic light means single frequency. You see how here in our stimulated emission, I'm only talking about a single frequency coming in. So that means by using an activation energy, okay, activating the laser, the population inversion inside the material, inside a cavity, I can create a monochromatic light. Okay, so there is a optical amplification is involved. How amplification is done? See, the laser, the lasing action means stimulated action happens in few atoms right now. They will emit. So those photons were made to go back and forth continuously. When those things go back and forth, they trigger few more atoms to de-excite stimulatedly. So the amplification, the rise of photons emission go to some peak value. Up to that point, the oscillations of photons happens between back and forth. After some time, okay, I can trigger to exit for this bunch of photons to come out of this cavity. So that is what optical amplification is. Okay, and this will compensate transmission losses. Okay, and so this transmission losses, if there is any the electrons going somewhere out of range, go to some unrequired orbits, those electrons may cause some loss in the energy that may also be compensated in this process. Okay, and this is very much important in the case of telecommunication these days, as the lasers are involved. Okay, and also the major devices. Okay, microwave amplification, the same process is used. And for example, in precision timing applications, in the astronomical observations also, this same population inversion process is involved. Okay, so population inverse is the fundamental departure from thermodynamical equilibrium that makes laser physics possible. Without achieving this condition, no laser device can function. Okay, so as you can see, that is the most important thing. Okay, so let me go further. So radioactive processes, okay, radiative processes. This is observed from Einstein picture, Einstein has described this. Okay, so I was just discussing earlier the absorption, where the electron jumps from ground to excited due to the absorption of the electron. How it is described is, it is described in terms of transition rate. Okay, rate of absorption, something like that, which is equal to Einstein's absorption coefficient, which is beta 12. Okay, so beta 12 is a absorption coefficient which directly depends on the population in the ground state. Okay, right? So and the rho of v represents the radiation density at the frequency. Okay, how much radiation we had put up. So this process develops the lower level populates the upper level. What I mean is, because with this process I can put the electrons from the ground to excited state. Okay, the other one mathematically, if I had to represent, that is rate of spontaneous emission. Okay, rate of spontaneous emission. What is that? It is now represented by Einstein's spontaneous emission coefficient, which is represented by A21, means de-excitation from de-excitation from 2 to 1, so which is directly proportional to N2. This time there is no light involved here. Okay, on its own the photons like are emitted with the de-excitation of the electron. So that is what showed with this equation. Okay, so this is called Einstein's coefficient for A21, called Einstein's coefficient for spontaneous emission. So the emitted photons have a random phase here. Okay, and direction I can't have a control. So this process limits the population inversion lifetime. If at all, somehow, if I happen to have excited electrons on the higher state more, let's say the ground state is less. You forget about how it is achieved. Let's say it is there. Due to the de-excitation on its own, I might lose the N2 more than N1 condition. If the electron started coming down, in that case, I might lose the effect. Okay, inversion effect. So that's why one usually needs to limit this kind of a spontaneous emission. Okay, right? So how it is done? It is something to do with experimental quantum optics. So we are not dealing much into it. We'll just take it for consideration. Okay, now when it comes to stimulated emission, this time you see the rate of stimulated emission. Okay, how it is explained or described mathematically, it is now B21 coefficient with a rho of mu multiplied by N2, where B21 is the Einstein coefficient for stimulated emission. Okay, and the population emission, the rate of stimulated emission directly proportional number of electrons on the excited state. Okay, so here emitted photons is coherent with incident photon. I just said earlier, coherent in the sense fixed path difference or phase difference would exist. The stimulated photons would have a same phase and direction and even polarization property of the incident photon. So even though what I explained earlier, this one, the incident photon is not consumed, but it plays a role in having a particular direction for stimulated emission photon and also the phase and polarization of the stimulated emission. So that is a very, very advantageous thing. Okay. So now, how it is done, by the way, right? For example, in the case of two-level energy system, let's say take only two-level system. Is it possible? That is a question, right? So in the two-level system, in a way, it is not possible at all. It will say impossible. Why it's impossible? Okay, so if you say absorption, photon energy, if the photon energy matches with, let's say, this is E2, this is E1, so reflection energy matches with the incident photon, so then I'll have populating the excited state with the electrons. Okay, and rate of absorption is directly proportional to n1. Okay, right? So I have more radiation field incident onto these atoms, bunch of atoms I can have. But the thing is, you see, by the time you are putting in the atoms on the excited state, on the other side, spontaneous emissions takes place. I can't have a control on that. So this is called a quantum mechanical decay process. It's independent of external radiation field and produces incoherent photons. Means in the direction without any specific direction, without any specific path or phase difference, they just exit out of the material. Okay, so there is upper limit for the lifetime as one more thing, that also one of the important factor. What I mean is lifetime is 1 microsecond. Within that time, I have to populate. Okay, if I go beyond, right, above my 1 microsecond, photon, the electrons start coming down. So one side I'll be populating, another side they're coming down. So these are the some of the features which stops us in realizing population inversion, that is high number of photons, electrons on the excited state. Okay, the stimulated emission, if you see, produces a coherent amplification, and the rate is proportional to the number of electrons at the excited state, okay, with the field intensity. So this can create a photon identical to stimulated photon. Incoming photon and outgoing photon we can be same. So this is a basic for the laser operations when it is dominant. But the thing is, even here, at the most, we can have a streamlined photon, but I cannot have laser amplification here. Means on one side, I'll be exciting, another side, they'll coming down, and then I'll have a stimulated emission. So that also, it's not going to help with just a two-level atom. For this, what people thought, let's go for three-level atomic system. Okay, so why population inversion? Population inversion is required to have more number of more number of stimulated emission emitting through the process. That is why we need a population inversion. Okay, so this is an explanation why it is impossible with the two-level atomic system. Now let's go for three-level atomic system. Okay, wait a minute. I have four-level atomic system also. Okay, it is not uploaded properly, but anyway, I can draw it here. Anyway, we have for a three-level atomic system, how it is done is we'll just take a three-level system. Now you see the energy differences are now nicely placed non-linearly. So let's say I have a ground state. I have first excited state and second excited state. Okay, right? So what we will do, we will couple this three-level atomic system to two laser fields. Okay, so two laser fields in such a way, there is a first field which couples between ground to second excited state. Let me call this as a 0, or let me call it as a 1. Okay. If it is 1, the second one is 2, the third one is 3. Now, the coupling of laser field, let's say a blue color laser, by frequency coupling to level 1 to level 3 transition. We can take it very, very strong so that most of the electrons from the ground, most in the sense, whatever maximum possible will be shifted to the straight away to the second excited state, that is level 3. Okay, so that is possible, we can do that. In that case, what happens? Electron starts populating in the excited state. Okay, now we can choose the transition of the electrons from level 3 to level 2 in a very fast manner, and also we can choose them in such a way a radiation is not emitted from there. 1 minute. A radiation is not emitted from there. Okay, so how I am going to choose that de-excitation? De-excitation can be done in such a way, right? So the radiation is not emitted and it also very, very quick. And we choose that mid-level in such a way the amount of separation is very, very low. Okay, right? So energy separation is low. What happens now? Electrons start accumulating in the level 2. Okay, now what we will be doing is, as we choose large strength pump field, more of the electrons go to the excited state, out of which, let's say now the ground state start reducing number of populations, and the highest state level 3 started populating, and from there we de-excite, like put them to the level 2. So what happens? The level 2 electrons start increasing, and they increasing in such a way, right? I started to see the electron number in the level 2 much larger than level 1. You see, this happens within the lifetime of level 2 excitation lifetime. Okay, so now if you just concentrate on only level 2 and 1, you see the level 2 n2 is going to be greater than n1. Okay, so the moment this happens, at that point what I do, I strike the atom with the slow laser transition. I'll strike the atom with the probe field with the frequency matching with the level 2 and level 1. So basically, what is the role of this probe field? The probe field is to stimulatedly emit the photons due to the de-excitation of the electrons from level 2 to level 1. Okay, so it's like there is a orange color probe field, there is a blue color pump field. Pump field may be very, very strong. Okay, right? So, but what exactly we are going to have is, we are going to have a lasing effect. The photons which are coming out with a frequency of separation between level 1 and 2, they may be coming in a very streamed fashion with a very good coherence, and I am going to have amazing streamlined photons with the coherence and also fixed polarization. Okay, so this is the population inversion leading to a lasing effect. Now, whatever emitted photon, how it is amplified, I just put this thing, entire thing, inside a cavity with the mirrors on the other side. So when I say mirrors, if I had put, which means I'm saying not only this single atom, I have put several such atoms. All the atomic vapor is coupled to a probe and pump field. So in that way, what happens? The excitation to the level 3 and then coming quickly to level 2 and having a population inversion between 9 n2 and n3 n1, and then we have a de-excitation. Okay, it is, in a way it is fine, it's a very good means to have a lasing effect. So it's a external source excites e to e1 to e3, and then we'll have a population inversion, okay, with the e2 and e1 producing a coherent photons. Okay, so what is the The example this process is used is in ruby lasers. Okay, right? What kind of a material is being used? It is also described what kind of a frequency we will be getting, our wavelength light we would be getting is mentioned here. Okay, now there is a challenge here. 50% population inversion, high pump power is required. Okay, right, to have a better population inversion. For that, what people thought, can we take instead of having 3-level atomic system, can we take a 4-level atomic system? Of course, it is possible. Okay, so what is this 4-level atomic system would look like? Okay, so 4-level atomic system would look like, 1 minute. Yeah, let me draw 4-level atomic system for you here. So just like a 3-level atomic system, what you will have between, okay, so there is one more here, between level 1 and 2 there is a one more. This time what I'll be saying is this one is level 1, level 2, level 3 and level 4. So this is a 4-level system. Now my pump field, a strong pump field will pump the electron. Let me take a different color. Okay, blue color. So pumping is done to the excited state. So pump field very strong. Okay, and from, okay, maybe I'll take a 3 also very close to the excited state. That is better. Yeah, 3. Now what happens? The electrons, excited electrons would decay quickly to the ground state. Sorry, next below state, very fast, radiation less transition. Okay, and now the lifetime of level 3 is chosen such a way, okay, very long lifetime, right? So when it comes to the level, like if there is any population is there in level 2, what we will do, we will take another quick decay from level 2 to level 1. So what I am doing here, I don't want any electrons residing in level 2, okay, but more electrons in level 3. That is what my target is. Now, whenever I had populated more number of electrons in level 2, that time what I do, I'll quickly incident a probe field, okay, a probe field, which is of what color? Yellow color, orange color or something. Yeah. So I'll couple with the probe field so that I would be having a stimulated photons coming between 3 to 2 transition. Okay. So here one advantage is, see, I can't reduce the ground state population for a very, very low value. It is always some number will be there. But when it comes to the 4-level system, I can make level 2 absolutely zero. No photons, no electrons whatsoever. So by doing it, the level N3 could be much larger than N2. So that is a far better population inversion than the 3-level atomic system. So that's why it's called a superior efficiency, efficient population inversion creating module or a mode. Okay. So the process is, first is a strong pump field from E1 to E4, and then non-radiative de-excitation from E4 to E3. And if there are any photon electrons are there in the level 2, those things are also made to come rapid down to level 3, level 1, so that I want to have population inversion between N3 to En2, level 3 to level 2. Okay, right? So the key advantage is, like I said, lower laser level E2 remains nearly empty, very close to 0. Okay, right? So dramatically reduce the threshold pump power. We can relax a little bit of pump power. Okay, because earlier with the 3-level atomic system, the pump power has to do even reducing the electrons in the ground state. So in addition to maintaining high population in the all the way level 4, level 3, here the pump field should be continuously doing the work and it should be very, very strong. That can be avoided in the 4-level atomic system. Okay, right? So it's a superior. In a way, there is a process called, you can trap the electrons in the level 3. So that is also called population trapping, which is in fact the process of quantum interference. What is a quantum interference? Let me quickly give you what is the process of quantum interference, how it is actually done, trapping, making a population more in level 3 than level 2 in the case of 4-level atomic system, or level 3 level 2 then level 1 in the case of 3-level atomic system. How it is done is using something called quantum interference. So what is quantum interference? Let me explain. Okay, what is quantum interference is, if I just take a 3-level atomic system, for the convenience I draw them separate slightly in the vertical horizontal flame differently. Let's say I have 0, I have 1, I have 2. Okay, now if the direct transition of electrons from 1 is forbidden, ground to excited state 1 is forbidden, means I can stop that kind of a absorption. So what I'll be doing is, I'll all the way excite the electrons to the excited state and make the electrons to go to level 3. Okay, right? Now in the process I am telling you, okay, how I am going to stop the de-excitation. Okay, how I am stopping is, okay, somehow I'll create a destructive interference of various parts of excitation from 0 to 1. Okay, so what are the various paths? What are the various paths is, going to level 1, probably if you just take a 3-level atomic system, direct excitation, and going from here and then coming back and then coming back and doing this. Okay, so this is 2 paths. If there is a direct excitation from 0 to 1 is possible, so that is there, and indirectly from level 2 to level 1. Okay, so let me show you that. I think the first process is this one. Okay, so this consists of transition to 0 1 and 2 to 1 and direct 0 to 1. Now you see there are paths. There is a path 0, there is a path 1. Not only that, I will have another path. What is the another path? Going and coming down, then again going back and then coming down. So this is a P3, sorry, P2. Now if you see, so given 3-level atomic system, if I combine and connect this 3-level system with multiple laser fields, okay, transition of electrons can happen between 0 to 1 in multiple paths. So all these paths will interfere, like a P0, P1, P2 and P3. All of them interfere. They interfere, it's just like interference, the Young's double slit experiment. Interference is going to give a constructive and destructive interference of the light, right? Similarly, the transition of electron from 0 to 1 directly can be somehow cancel, and the destructive interference may happen. The electrons will never excite directly from 0 to 1. Only excitation or populating 1 happens through level 2. So that is a quantum interference for you. This is a multiple paths interfering and leading to cancellation. So that is called quantum interference. Okay. So here the population inversion is one way of doing it, and using trapping the electrons in a mid-level is another way of doing it for the population inversion. Okay, right? So there is also something called electromagnetic induced transparency that is also arises due to this phenomena. What is that is, I can make the atomic vapor become transparent for a particular incident field, never ever observe that field. For example, what I draw, the transition between 0 and 1 never happens, which means if there is a transition frequency is, let's say, omega 01, okay, if any light is incident, with this frequency, that light never is ever going to be absorbed. It just transmit as it is. That is a induced transparency for a given light. Okay, when I have a population trapped in level 1, having no population, if there is a population that may populate, that may go between 0 to 2, but never to 0 to 1. So in that way, we can induce the electromagnetic induced transparency. So when I talk about the process of population inversion, means there are multiple ways I can perceive it. One is population trapping, Another one is EIT, electromagnetic induced transparency. Okay, right? So most important thing is excited any level if I choose, that must be larger than the ground state. If I happen to have, then I would say that is a population inversion for you. Okay, right? So let me see what I have further have in our, yeah, it's a thermal. This is all we discussed. Okay, so population inversion we just discussed in detail. So let me go to discard. I don't want any written things. Let me go and show you what is a Josephson effect. Okay, so that's a part of today's session. We want to discuss that. What is a Josephson effect? Josephson effect is, if I happen to have, okay, right, if I happen to have a superconducting material, okay, right, a superconducting material means a material where if I cool the material to absolute zero temperature, okay, in that case, what should I have if I connect that superconducting material to a battery? Let's say, in that case, I should be able to see current flowing through that without any resistance whatsoever. Okay, so usually when I have a conductor, when I connect to a battery, there is some resistance. Obviously, due to the electrons traveling through the conductor hits the other ions and some other ions and do collisions. Because of that, the resistance, the temperature of the material increases. That itself again triggers the collisions, and then resistance for the current would happen. Okay, but such a things can be completely removed from the material if I take a material of supercurrent or a superconducting and then cool it. Okay, so here it says, if I have such superconductor, one superconductor, in between there is an insulator, there is another superconductor. Okay, right? Let's say the question is, first question you can ask yourself, first of all, how is the superconductivity happens? That is happens due to something called Cooper pair formation. We will see in the next slide. Let's say for time being, the conductivity is there at a zero resistance. Now, Josephson effect means I take one superconductor in between insulator, another superconductor. If I take a sandwich, now what happens is, insulator by means it should insulate. It should not conduct any current through it. But even without any problem, the current would conduct through the insulator when I have the superconducting sandwiching insulator. Okay, so that is the Josephson effect for you. So it's a macroscopic quantum phenomena. This effect demonstrates quantum mechanics operating at macroscopic level, scale through phase coherence of a Cooper pairs. We'll just see what is a phase coherence. Just a minute. We'll see what is a phase coherence in the later slide. So in a way, it is a foundation for quantum technology, because right now squid magnetometers being implementing them, and also the superconducting qubits were purely based on this Josephson junction based inductor. Okay, so right. And also, if I have to measure some voltage with the standard values, if I have to fix in a circuit, I can use this equipment to fix the standard voltages. Okay, right. So the physical foundation for Josephson junction, what is that is, usually when I have a material, let's say a conducting material, electrons are there in its valency orbit. Okay, unpaired electrons are there in this valency orbit, which means the pairing is done in the inside orbits. What kind of a pairing? Inside the orbits, the pairing is done with the electrons and its magnetic moment opposite spin. What I mean is, if I just take electron is revolving around its own axis in such a way, the current constitute is anti-clockwise. In that case, magnetic moment would be north and south. It's like a small bar magnet arranged like this. If the electron is having its electric current in the opposite clockwise direction, in that case, its corresponding magnetic moment would be south north. Okay, so now if we just take these electrons revolving clock and anti-clockwise, bring them together, it's like two opposite spin bar magnets put together, they attract. So in that way, the pairing may happen with the opposite spins in the orbit. Okay, but there is another way of pairing can also happen in the case of superconducting material due to the phonon interaction. What is the phonon interaction? Is a vibrations inside the material. Okay, so the nucleons cannot move, but they may vibrate. Due to that interaction, what this phonons does is they may create some kind of a transition paths for the electron to go through the material for current conducting in such a way, right? Let's say there is a streamline path is there for electrons to flow, so they may flow like as per their wish. But as due to the phonon interaction, there are locations where very stream path, very minute path is created. At that location, what happens? The electrons were put to go together as if they are paired. Okay, so that is where we just see electrons appear to make a pair. It's called a Cooper pair. At that point, you know what is the total charge of the Cooper pair is 2e, and they are going to possess a spin, zero spin. And electrons by nature, they are fermions. When they combine and pair up, they become bosons. So spin is zero there. Okay, so right, so they condensate into a single quantum state together. Okay, how? If I have individual superconductor, if I just take a single electron, superconductor case, okay, it is going to pair up with another electron, going to form a Cooper pair. So that I am going to represent in terms of wave function, where the absolute square of a wave function would tell me how much density of that Cooper pairs are there in given location. And this density would vary along the material with a phase of exponential I theta. Okay, where theta is a macroscopic phase. So just like if I put an electron inside, let's just take simple example. If I just take a one-dimensional box, 1D box, if I just place an electron inside a one-dimensional box, what happens? You see, the electrons not only behaves like a particle, it also shows a wave nature, as if some kind of a wave is created between these two ends. Now, you take absolute square of the wave nature. Okay, you take absolute square. What you do from the absolute square, you can find what is the absolute location of the electron in terms of probability density. So that is the role of absolute square for a wave function. Similarly, the absolute square what we have in our macroscopic wave function in the case of Josephson junction is, this is the density of the Cooper pair, okay, like probability wise, and how that is going to change is represented by exponential I theta, where theta is a macroscopic phase. Okay, now I'm having a sandwich of both of them. Sandwich, right? The left hand side superconducting, right hand side superconductor, middle is insulator. Now say left hand side is phase is theta 1, right hand side is theta 2. Okay, there is exists a phase difference between Cooper pairs from the left to right. So that kind of a phase difference is rises. That is going to create a one interesting way of current through this junction. What is that? Is showed here. Okay, what is the Josephson effect? Which is showed it as current would have some critical value, and that critical value will be fluctuating from some minima minus IC to plus IC with a phase. Okay, what is this phase, by the way? This is a theta 1 minus theta 2, that phase. So basically you are going to have a current through this entire thing, which I is equal to IC sine phi. Okay, fine, that's very good. So it's a AC Josephson effect, means current going through back and forth. That is AC. I can continuously have a current going in one direction. That would be in a DC Josephson effect. Basically, what it is cost is it is cost you to sandwich one more thing, how much voltage you are going to put up across the junction. Okay, you are going to connect to the battery here. Okay, so whatever is the battery you are going to connect, what is the battery voltage would decide, okay, how much rate of phase change would happen. Okay, every other thing is the Planck's constant, electron charge, they are like quite common. Okay, so by just controlling the voltage, you can have the current oscillation with what frequency it has to oscillate, that I can control. So when it comes to application, the standard voltages we can realize out of this Josephson junction, and also you can create something called extremely precise V voltage versus frequency relation, and there is something called Shapiro steps under microwaves. It's like advanced field we are not going to touch, and also in the metrology application it is being used. Okay, right? So how it is useful for us in quantum technology? How it is useful in quantum technology is, I'll quickly show you. If I'm going to have an inductor and a capacitor together, if I connect that to, let's say, oscillatory voltage source, this is going to create for me, even if I don't have oscillatory field, it's going to create a single oscillator of voltage or oscillator of capacitance charge. Okay, in such a way I am going to have capacitor being charged between certain states. What kind of a states? I can just give you a simple example. Let's say 5 coulomb, 10 coulomb, 15 coulomb, 20 coulomb, and 25 coulomb. So I'm just only talking in terms of in what states of capacitance is going to be exist in time at different times when I have such a circuit. You see here the quantum mechanical separation between any two states is equal. That's why it's called linear separator. Okay, linear oscillator. Okay, so if I have a naturally occurring atom, the quantum mechanical orbits, you see, they're unequally spaced. So if I happen to realize a qubit out of this, I always lose the quantum information between any of the two levels, because any of the two levels is equally spaced. Okay, so but in real natural atom it is not there. So in that case I am able to realize a qubit, but there is a problem. There is so much fragility in the real world atom. For that I need to realize the real world atom artificially. So for that I can use a LC circuit. Okay, but in the LC circuit the states are equally spaced. What people thought is you replace this entity inductor with a Josephson junction. What is that? It is represented as like this. Okay, superconductor, insulator, and this such a superconducting junction is going to have a energy is a Josephson junction energy and some potential depending on the phase. Because of that, I am going to have a non-linearity coming into the case, into the charge states of the capacitor. What I'm going to have is probably the charge states of the capacitor would be something like that. 5 coulomb, next one is 10 coulomb, Next one is 15 coulomb. Sorry, not 15. 1 minute. 5 coulomb straight away. Next one is 15 coulomb. Next one is 18 coulomb. Next one is, let's say, 19 coulomb. So the separation is here is 10. Next separation is 3. Separation is 1 coulomb. So in this way, we can have a non-linear energy separation between the voltage states of the capacitor. In that way, I can realize a qubit perfectly. So that's why Josephson junction is going to play a very, very vital role in the case of qubit realization. So if I have to write down the Hamiltonian for that, means the total energy state of Josephson junction inside a capacitor LC circuit, which is going to have something like this. This is a capacitance energy. This is a Josephson junction energy. So if I try to find what are the energy eigenvalues and eigenvectors of this, if you find through a quantization, you are going to get a nice uh, non-linear energy states, what I was explaining here. Okay, and corresponding energy states also you will be getting. Probably in the next session we will touch how to do that. Okay, right? So let me summarize for today. What did I discuss is, I discussed about what is a population inversion, how it is done in 3-level atomic system, how it is done in a 4-level atomic system. Okay, and what is a Josephson effect, superconducting sandwich, and how it is important in the case of superconducting qubits that we discussed today. Probably in the next session, we will see some mathematical description in detail. Okay, so let me see a question here. At 428, there is a question. Quantum states are fragile. Noise affects the communication and population inversion. Isn't that a limitation? Of course, that is the limitation. So that is where we have to protect our qubits, quantum states, inside a cryogenic cryostats, where they are not interact with the surrounding. When it comes to traveling, in the case of communication, you know what they do? They take the quantum state fed onto the flying qubits. Photons are not that much affected by environment when they're traveling through a waveguide. In a quantum mechanical form, they can travel. We can launch them through a waveguide and they travel. Okay, in that case, I may not be relying on any population inversion. I'll purely rely on population inversion when the lasing effect is required to create a photons, a bunch of coherent photons. I would be needing a laser inversion, that is a population inversion. When I create a superposition state, I feed it onto the, let's say, LCR circuit inside a chip, superconducting chip. I do some quantum gate operations. The result, let's say I want to send it somewhere else, I'll feed that result onto photons, and photons will travel and they just communicate. Okay, right? The limitations are there when it comes to noise coming from the interaction from the environment. That needs to be taken care by shielding and reduce the temperature with the cryogenic liquids like liquid helium and nitrogen or hydrogen. Okay, so managing the inversion is a tricky and complex. How can we make this more perfect? So I just explained to you earlier, using 3-level atomic system and 4-level atomic system with 2 fields. One is pump and probe field. We can do that. Okay, right. Josephson effect happens at room temperature or 0 degree Kelvin. Good question asked. There were claims some time back, like few years back, we can have superconductivity at the room temperature, but that is not in general possible. As of now, as far my knowledge goes, to have a superconductivity, we need to go at least a millikelvin temperature. Okay, not absolute zero, may not be needed, but millikelvin at least, or few kelvins at least, which means Josephson junction, as Josephson effect also needs to reach to that few Kelvin temperature. Okay, right. Single photon laser is 4-level laser. Right. So single photon laser is no, lasers may give multiple photons, out of which you have to take few photons out of it. Probably you do attenuation effect, means some kind of a reducing the number of photons coming through the source. Basically, what you do, you put a filters. Okay, so it's like you are diminishing the intensity of the light coming from a laser source. In that way, you are going to get a few photons. So there are various technologies have been used to attain single photon level or single photons from a stream. So it can be possible a 3-level atomic system or 4-level atomic system. 4-level is just an advanced and superior version when it comes to 3-level atomic system. There are different kinds of lasers are available. There may be a 3-level atomic system based lasers or 4-level atomic system based lasers. Okay, right? So that's about for today. So since 1 hour, so I just quickly covered these two things. Probably in the next session, which I'm going to have, I think I'm going to have back-to-back sessions, which is on 14th. Yeah, it's on 14th. So probably if there are any questions, I'll touch on that. So in that case, I'll discuss a little bit more on quantum mechanical phenomena, that is measurements, how it is going to put some standard limitations quantum mechanical wise. So during that time, I'll address few more questions if there is any. Okay. So thank you very much. I'll be sharing the PPT in the Canva. You please check. Fine. So yeah. Can you share the presentation and the whiteboard discussion? Yeah, I'll do that. So I have not done much, probably. Yeah, I'll share. Yes, thank you. Okay, so I'll hand it over to Ken. Yeah. Yes, sir. Avasti, sir. Please take over.
So, sir, I hope you have already responded the queries, because
Yes, I did.
so if there is no other queries, sir, I think 1D box electron explain.
Yeah. Okay. 1D box electron explain. Okay. Okay. So what is a 1D box? Huh? Okay. 1D box is, okay, let me give you. I already discussed, but I will do it once again. Okay, let me do it fresh. Okay, so just to take a one-dimensional box means, okay, let's say x is 0, x is L. So electron, if there is anything which is put inside, it is only have possibility to go left and right. Okay, so because of the such a small size, this electron, it's a material by nature. It's not only exist as a material, it is also shows a like a wave. How do I know it's like a wave? Right? It's a material for me by nature. How do I know? What I'll do, I'll start find like making a measurements, means trying to see where the electron is located in this box. Okay, where it is located in this box. Let's say I'll make 1,000 observations, means I'll look at x is equal to 1, x is equal to 2. Okay, so at every location I'll start looking at the whether electron is present or not. Interestingly, what I find, the electrons start appearing with a greater probability in some location, absolutely no probability, right? Something like that. Okay, what is this is, there is a location, right? There is a location, electron is found maximally, there is a location, maximum location, maximum, there is a location, electron is never found. It's a probability distribution, like so out of 1,000 times, probably 300 times it is found. Probably it found 1 or 2 times here, let's say 5 times, let's say 100 times, like that roughly. So if I combine all of them, I'll get 1,000 times. So this kind of a probability distribution is there. People thought, how to understand this probability distribution? Let's say this is some kind of a function g, okay, with respect to x. If you just take absolute square root of the square root of this, what you are going to get, square root of this is you are going to get f of x plus or minus. What is that? It is going to be something like this. I am just trying to understand from the wave nature. What is that? So the f of x, this is a positive part of the f of x. This is the negative part of the f of x is a function. This is again positive part of the. Okay. So that is what this is the wave. It's just like a standing wave. If I tie a rope between this end to this end, I create a small wiggle at this distance. That wiggle travels to the end and then travels back like a standing wave pattern. Okay. Now, if I take absolute square of that, that is what I got. Now, this is the probability distribution. This is a g of x. Probability distribution. Okay. So, which means the electron presence inside a material showing some kind of a hilly probability distribution. If I take absolute square of that, it shows a wave kind of a behavior, which means electron by nature is going to show a wave nature like a standing wave pattern like this. Not only that, there is one more connection. What is that one more connection? Yes, if you find the wavelength of this wave nature, lambda, which is going to be indirectly proportional to the mass and velocity with which the electron is moving inside this box. Okay, so h divided by mv, this is actually de Broglie wavelength. So which means if the mass of the particle is so small, it can move with the velocity of the light. In that case, it can have measurable wavelengths, something about minus 10 to 10 to the power of minus 15 meters. So this is an optical frequency range, measurable range. If you have any other, let's say larger particles like a bullet, if I fire a bullet inside this one-dimensional box, it's traveling in a forward direction, let's say, in that case, I never have a wave nature. Okay. But if I go to a electron, a small electron, mass of the electron is something of 10 to the power of minus 34 kilogram, and velocity could be 10 to the power of 8 meter per second. If you put that into here, see the numerator is 10 to the power of minus 34 Planck's constant. So that is where you are going to get a optical frequency wavelengths or optical light range. Okay, so one dimensional box going to tell me the electron is going to exhibit a wave nature. Otherwise it is going to be a simple particle. If the bigger the particle, no wave nature. Smaller the particle, wave nature is there. Where I am going to use a wave behavior. So why did we come across this? Because, okay, so we are talking about wave nature for a Cooper pair. Okay, so Cooper pair could be not a single electron, it's a combination of two electrons. So two electrons together is dictated by the absolute square of that wave function of the two particles. It's like a density. How many Cooper pairs are there in a given location? So that instead of just a single electron in a given location, this time in the case of superconducting material, we talk in terms of how many coupled electrons are there in particular location, which is described by, okay, a wave function is described by absolute square exponential I theta. Okay, no, not absolute square, absolute value. Okay, fine. So that is a one-dimensional box description. Why do we need it here? Fine. Fine, sir. Kamlesh sir, I have.
Yes, sir. Perfect, sir. So thank you, sir, for your time and very fundamental lecture. I hope participants have enjoyed it. And as you mentioned, so we are having other sessions by you shortly. So once again, on behalf of participants as well as our own these coordinators, I thank you, sir, for giving your time and this lecture.
Sure, sir.
Thank you, sir. Thank you, sir.
Sola sir is there. Hi, sir. How are you?
Thank you so much, sir. Nice to see you.
Same here, sir.